Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test held in the month of March 2025. It is a rescheduled examination for Assam Center. In this video, we discuss the solution of a problem from the section Real Analysis, and the problem is related to the fixed points and uniform continuity of a given function with given conditions. This question is placed in part C, which is a multiple select question. There may be more than one answer, and the question carries 4.75 marks. The question ID is 706543. Further, this question is suitable for all these examinations. Right. The given question is, let F be a map from the interval 0 to infinity closed at 0 and to itself be a continuous function such that limit extends to infinity of f of x by x is equal to alpha less than 1. Let S be the set of all C belongs to 0 to infinity, the interval 0 to infinity, closed at 0 and such that f of C is equal to C. That means S is the set of all fixed points of f in the interval 0 to infinity. Which of the following statements are true? We are given four options. Option 1, S is empty. Option 2, S is non-empty. Option 3, F must be uniformly continuous. Option 4, F need not be uniformly continuous. Right. Let's now discuss the solution of the problem in detail. We are given a continuous function from the set of non-negative real numbers to itself, satisfying limit extends to infinity f of x by x is equal to alpha less than 1. Given S is the set of all those elements C belongs to the interval such that f of C is equal to C. That is, S is the set of fixed points of f. And the first two options ask us, is S empty or S non-empty? Now, limit extends to infinity of f of x by x is equal to alpha less than 1 will imply f of x is less than x for large values of x. Right? Limit extends to infinity, f of x by x is less than 1 will tell us f of x is less than x for large values of x. Therefore, there exists a m greater than 0 such that f of x is less than x for all x greater than or equal to m. Yes. Now, what we have is f is the set of non-negative real numbers to itself. This implies f of x is non-negative for all x belongs to the interval. We have two cases to deal with. Case 1, f of 0 is 0, then g is a fixed point of f, and thereby S will be non-empty. Case 2, f of 0 not equal to 0. Then f of 0 will be positive. It is not 0, therefore it is positive. Right. Now let g of x is equal to f of x minus x. Clearly, g is continuous on the interval. Why? Fx is continuous, x is always continuous. The difference of two continuous functions again continuous. Note that g of 0 is equal to f of 0 minus 0. That will be f of 0. But f of 0 is greater than 0. We are dealing with case 2. And g of m, x is greater than or equal to m. For x is equal to m, f of m less than m. And thereby f of m minus m will be negative. Right. So what it is, for g of 0 it is positive, for g of m it is negative. Therefore, by intermediate value theorem, there exists a C belongs to the open interval 0, m such that g of c is equal to 0. Right. That means f of c, g of c means f of c minus c is equal to 0. That means f of c is equal to c. That means c is a fixed point of f, and thereby S is non-empty. And in any case, in case 1 and case 2 put together, S is non-empty in any case. Thus, we have these two options. Option 1, S is empty. Option 2, S is non-empty. So, option 2 is true and option 1 is not true. Agreed. We continue discussion in the next slide for uniform continuity. Right. Option 3. F must be uniformly continuous. Option 4. F need not be uniformly continuous. F has these properties. F is a map from here to here and is continuous and satisfies limit extends to infinity of f of x by x is less than 1. Such a f, is it always must be uniformly continuous? Or f need not be uniformly continuous? To establish option 4 is true, you look for an example of a function satisfying these conditions and show that it is not uniformly continuous. Then 3 will be false and 4 will be true. So for that, we look for a counter example. Let f of x is equal to alpha x plus sine square x square, where 0 less than alpha less than 1. Clearly, f maps from the interval 0 to infinity to 0 to infinity, and it is continuous because alpha x is continuous, polynomial, it is a sine square x square is continuous. The sum of two continuous functions is continuous. So what about this condition? Further, limit extends to infinity of f of x by x is equal to limit extends to infinity of f of x is alpha x plus sine square x square by x. And alpha x by x is alpha. Limit of that is alpha only. Limit extends to infinity of sine square x square by x. This will be 0. Why? Why? Limit extends to infinity of 1 by x into sine square x square. Sine square x square is a bounded function. And limit extends to infinity of 1 by x is 0. So therefore this is 0 and you get alpha. alpha is given to be less than 1, taken to be less than 1. So the conditions are satisfied. So for this function, our claim is f is not uniformly continuous. For this, we recall the sequential criteria for uniform continuity. A function f from A to R is uniformly continuous on A, which is a subset of R, if and only if the sequence f of xn minus f of yn converges to 0. Whenever the sequence xn yn is in A or such that the sequence xn minus yn converges to 0. Define the sequences xn n greater than or equal to 1, yn n greater than or equal to 1 in the interval 0 to infinity, where xn is equal to under the square root of n pi plus delta and yn is equal to under the square root of n pi, where delta is positive, and get it fixed. Right. Now xn minus yn is equal to xn under the square root of n pi plus delta minus under the square root of n pi. Rationalize the numerator, multiply and divide by root of n pi plus delta plus root of n pi, multiply and divide by that. Then the numerator will be delta, because n pi plus delta minus n pi cancels, delta will remain. In the numerator, in the denominator, it will be root of n pi plus delta plus root of n pi, not minus. It is plus. And this tends to 0 as n tends to infinity. There is a typographical error here. Right. So as n tends to infinity. Right. Correct. Now what happens to f of xn minus f of yn? This also tends to 0. Then this sequential criteria for uniform continuity can be applied. And f of xn minus f of yn is equal to alpha times root of n pi plus delta minus root of n pi. That is alpha xn, alpha in brackets xn minus yn plus sine square n pi plus delta minus sine square n pi. And sine n pi is 0. N is a natural number, it will be 0. And this is plus or minus delta you will get, but it is a square. Therefore, plus sine delta only you will get. This will be sine of n pi plus delta will be plus or minus sine delta, but it is square. So it is sine square delta. So this will be 0. So, but this is as it is, alpha into this plus sine square delta, and this tends to sine square delta only, because root n pi minus under the square root of n pi plus delta is 0. This is 0. This is 0. Right. So it will tend to sine square delta as n tends to infinity. Now choose delta is equal to pi by 2. Then f of xn minus f of yn is 1. As n tends to infinity, converges to 1. Why? Converges to sine square pi by 2, that is 1. As n tends to infinity, when xn minus yn tends to 0 as n tends to infinity. Right. So that means f of xn minus f of yn does not converge to 0 when xn minus yn converges to 0 as n tends to infinity. So the sequential criteria for uniform continuity is if and only if statement. It is violating the condition, therefore it is not uniformly continuous. Therefore, by the sequential criteria, f is not uniformly continuous. Right. So here is a function f satisfying the conditions, and f is not uniformly continuous. Therefore, if you say f must be continuous whenever f satisfies these conditions, we do not will not have any function which is not uniform. Because it is not uniformly continuous, f must be uniformly continuous is not true. And when these conditions are satisfied, this f is not uniformly continuous. This is sufficient for us to say f. There may be functions which may be uniformly continuous. But here is a function. What we have shown you is not uniformly continuous. Therefore, f need not be uniformly continuous. Thus, option 3 is not true and option 4 is true. Right. And the answer to this question, options 2 and 4. That is the detailed discussion of the solution of this problem. It's a good question, but I rate it as a difficult question. As far as the exam hall is concerned, in the exam hall, it will be a difficult question. And especially getting this type of example will be difficult. Anyway, it is my personal opinion. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Yes. I'm sure we are going to meet you, all of you, once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thanking you.